the same rules apply for our afternoon session as the morning session, which is since we don't have ideal visual feedback on who's raising their hand or who's interested in asking a question, we really encourage you to sort of type in the chat asking the technical contact to speak up on your behalf, or else that you just go ahead and unmute yourself and ask your question. Toby is open to interruptions and questions as he's presenting, and Jeff is as well. So for the whole afternoon session, you should just feel just feel encouraged to please ask your questions when they arise so that we can have some discussion and make this more of a workshop, less of a lecture. We have 3 talks for this afternoon. After these remarks, Toby will present this generalization talk, and then we have our 2 case study talks, one from Jeff and one from Toby, with an idea of leaving some time at the end for general discussion and revisiting things, and for me to point you to the GitHub and ask your support and participation to make a little bit of a resource that we can all use as we think about this literature and delve into it a little bit. I'll show you some of the nascent efforts on that behalf if we have time, but that's basically the way it's going to work. There will not be a formal coffee break since we have such a short time this afternoon. I know some of you are going to need to take a break or get a coffee or use the washroom. Just kind of do it when it makes sense. And because we're going to kind of just have a couple of minutes of transition between the speakers and try to get as much time give them as much time as possible to share their content with you. So any questions before we get going in the room? Anybody online who has a question, please speak up. Okay, so we're going to turn things over to Toby.
Okay, thanks, Britt. Yes, great. It's good to be sort of giving this talk after Steve's great introductions to some of the kind of more kind of pure category theoretic topics earlier. And it's kind of a strange thing to be doing, to think about generalization, I think, at this point, because really kind of category theory is, I mean, even just a basic notion of category is so sort of general. But to some extent, this generality is kind of quite austere. And so it makes, I think, a bit of sense to kind of give a bit more structure and to see kind of some of the things you can do, and to be exposed to some of the tools that we use when we actually apply category theory in kind of the real world, if you could think of it like that. And so what I'm going to do now is go kind of a little bit further than Steve did in some generality, staying kind of more on the kind of pure category theoretic side, with kind of hints towards applications. Of course, we'll see more of those later. And because I've only got say 45 minutes or so, it really is going to be kind of a little bit of a whirlwind talk. But for that reason, I really reiterate that it'll be good to kind of, if people get confused or have questions, to kind of jump in. I've only got 18 slides, and although there's plenty of content, it'd be nice to have some discussion. And so whereas I say these are kind of advanced topics, they're kind of only kind of slightly more advanced. This kind of hierarchy of categorical structures kind of goes arbitrarily deep. It's really kind of infinitely sort of deep rabbit hole. I don't want to get too far down it, but I think it's good to make a little bit of progress. Okay, and so this is my slide changing. Yes. Okay, so as I was indicating, and I think we saw in the kind of introduction to this workshop earlier, much of the power of category theory and categorical methods stem from their generality and their kind of wide application. And as a result, category theory is the kind of mathematics of pattern and structure and interaction. Of course, pattern is like structures that are preserved across different phenomena. And because we have this notion of morphism, of arrow between things, it's really kind of patterns and their interactions. And so that's kind of really nice. And it's really nice for a kind of a reason that I hinted at the end of my introduction as well earlier, that it emphasizes concepts and systems not just on their own, but in context of other concepts and systems. And I think that's really important in the world today, that we think of ourselves as kind of connected to each other and to the world and to the environment around us, and rather than just kind of sort of atomic in some sense. And so I really think that categorical thinking is kind of appropriate for our age. But of course, each category is like a collection of things that are somehow similar. And in that respect, they're kind of like mathematical universes of their own. Each kind of inside each kind of these universes, there's kind of a language of things you can say about the objects. This is this kind of notion that I will mention a little bit about, and that's prevalent in a lot of categorical literature, the notion of internal language. And if we kind of adopt it to express statements about phenomena, about systems, about concepts, it kind of forces us to be very clear in this kind of phrase, well-typed. You can't really say things that don't make sense because you can't really compose two morphisms unless they kind of, if you have X to Y to Z, you have to have this Y on the domain and codomain. So if there isn't Y, you can't compose them. You can't make a thing. You can't make a statement that doesn't make sense in this way. And that kind of makes it, it makes it harder to say kind of informal things somehow. It forces us to think more clearly, but it, as a result, makes it easier to carve nature at its joints. And it also, it also makes it easier to see when things are somehow non-compositional or somehow maybe emergent. I often think that emergence or non-compositionality is like a shadow of some high dimensional structure. And so that's why some of the hierarchical things that I'm going to say might be important. And I think I want to make one other point, which is that this language, this internal language of a category often comes with some nice graphical calculus. We often draw diagrams of things, of systems or concepts and their interactions. And often these diagrams are informal, but because the diagrams here are obtained from the structures of the ambient category of objects we're interested in, and they come along with rules, like we saw the kind of rules of composition in the category, other rules like that. This language is not just powerful, but it's kind of very sort of descriptive. It's kind of very intuitive and descriptive, and kind of makes use of our big visual cortices. And as we've seen hinted in a number of places today, category theory, because of this kind of these kinds of, we've seen that we have higher dimensions in things like natural transformations, is able to sort of describe itself. And that's the thing I'm going to come to next. But before I do that, I want to say that it points towards something that we might think of as a sort of synthetic perspective on scientific statements. We start with these really sort of basic things, just objects and arrows between them. And it seems strange to be able to build complicated things out of such a simple structure, but we really can. And if we can build everything out of just objects and arrows, it's kind of this word synthetic, then we have this kind of maximally clear understanding of things. And of course, we're not always in that situation, but it's maybe something that I'd like to aspire to in my own work. Okay, so in the remaining, I don't know, 35 minutes, I'm going to kind of try to introduce this synthetic approach and build up to this notion of well-typed science, and emphasize the importance of seeing things in perspective and in context. So the first thing we're going to come to is have another look at two categories, this higher dimensional thing that Steve was talking about earlier, and how we can sort of generalize that notion and, as I say, go further down this rabbit hole of hierarchy. And one of the tools that we can use to do that is something called enriched categories. Now, you don't have to know what that means right now. I'm going to explain it. But it shows again how category theory makes very, everything, it seems, somehow can end up with some kind of categorical description. And some surprising examples crop up if you use the notion of enrichment. And so throughout, I'm going to be looking at examples. Many of them are sadly still quite mathematical. They're not all kind of day-to-day or cognitive. And this is one of the things I hope that will change as months and years go by. And I hope people in this community contribute to that. But in these examples, they're not just going to be kind of mathematical in algebraic symbols or things like that. They're going to be using often the kind of diagrammatic calculi that I mentioned earlier. And if there's time, I want to say a little bit more about these universal constructions that Steve was talking about and how they're related to this kind of notion of perspective. I drew this little diagram here. This is like this is one of the kinds of components of a graphical statement in one of these calculi. This is like something we might think of like a sort of parameterized process. Somebody asked earlier about conditional morphisms. This is like something which has like inputs and outputs, but it also has like some kind of higher data coming into it, like some kind of parameter. And this is like a formal object. So it's kind of a two-dimensional thing. It's not just an arrow. It's kind of got some other thing coming in like a third dimension. Okay, but before we get on to all that, I want to talk about the archetypal two category, this category of categories. It's this two-dimensional object, as we saw earlier. It has objects, which we might call zero cells. I'm going to refer to them in this kind of way because it makes this sort of dimensionality very obvious. It's a zero cell because it's zero dimensional. It's just like a point. Those are the categories, the objects of cat. It's also got one cells, so between two zero cells, we have this thing which is one dimensional. It's a line. And here, these are the functors. We've also called them arrows or morphisms. And then, we've got arrows between arrows. This is the thing that I've called two cells here. And these are two-dimensional. So if we have two of these arrows, I've drawn this picture on the left, but I'm drawing it up again here on the right as well. If we have two of these arrows, these functors, we have a way of sort of filling it in, or we may have a way of filling it in with this kind of two-dimensional arrow. I've labeled it here alpha. It doesn't really matter. And this is a thing that's called a natural transformation. It's something that satisfies this diagram. So that if you've got any, if we're in this category, we've got two categories C and D, and we've got these functors F and G. A natural transformation alpha is a collection of arrows like this in D, because of course F and G both land in D, labeled by the objects of C, so that if you've got F and G applied to X and F and G applied to Y, you've got alpha X between the X ones and alpha Y between the Y ones. And the thing that makes it a natural transformation rather than just a sort of collection of arrows is that for any arrow F in this original category C, a square like this commutes. And so this says that you can go around this way or this way, as we saw earlier, and the two things are equal. Now, this is one two category, is the two category cat of categories, functors, natural transformations. There are many, and I'm going to kind of focus a bit more on just the kind of abstract structure. And so just as we saw earlier that there are axioms for categories, there are also axioms for two categories. They have the same kind of flavor. So they're just the things that we need to make composition make sense, that sort of make sense in this two-dimensional way. So we've got the sort of horizontal composition, the composition of the sort of one cells or arrows, and we can compose two sort of diagrams like this. And so we have to be able to say, how do we compose the two cells along horizontal composites? And so we have to make sure that these natural transformations sort of cohere with this one cell composition. So we call that horizontal composition here, but we also have this vertical composition. So if we've got functors or one cells F, G, and H, and we've got an alpha from F to G and a beta from G to H, we should also have a kind of composition rule just going vertically. And there are some other axioms which say that these things have to sort of behave nicely all together. As I say, it's kind of the same kind of set of ideas as we had in the one categorical case. It's just the obvious thing that you would have to do to make it apply in 2 dimensions. You could also go further up into 3 dimensions or 4 dimensions or sort of n dimensions. I'm not going to go much into that now. It's kind of the same idea kind of repeated. It gets quite complicated, as you might expect. And so you sometimes see things like, this 2, 1 category. And then there's this extra number here, this 1. And so what's this? It says that in all the dimensions above the first dimension, you can sort of invert these arrows. So we heard people asking about arrows with sort of heads at both ends. And this is kind of this concept. In some cases, it's useful just to have, always invertible arrows above certain dimensions. Again, I'm not going to get into this very much. I just wanted to flag it up in case people saw it in their reading. Now, there's another way of thinking about higher categories like this, 2 categories in particular, which is this notion of enrichment. So we saw earlier that a category C has a set of objects, which I write as C0, and for each pair of objects A and B, a set C from A to B, like written like this, of morphisms from A to B. Okay, so that's fine, it's a set. And now we saw earlier also that set is a category. It has objects being sets and arrows being functions. And so we might ask, what if we replace the set CAB with another kind of object, say an object in some other category V? Now, this is something, assuming that V has the nice enough structure, something that I won't say too much about, but kind of relatively common structure, enough to say, okay, we can put objects side by side using a product that Steve was talking about. If we have this category V, then we could sort of say that a category or a V category has a set of objects, and for each pair of objects A and B, an object, a V of morphisms from A to B. Now, of course, this just means that in the normal case, a category is really a set category because it has sets for the HOM objects, we might call them. Sometimes people call these things HOM sets because morphism is sometimes a shortened form of homomorphism. I'm pointing out at this point here that there are some axioms to ensure that the two kinds of composition, say the composition in C and in V, kind of play nicely together, just as we saw before. I'm just trying to give an idea of enriched categories at this point. And so I don't want to go into too much detail about what these axioms are. As I say, basically it says something like we need to be able to make a statement like if we've got a morphism from A to B and a morphism from B to C, then we have a sort of composition rule that allows us to go from A to C. And of course, this thing has to be an arrow in V itself. And so this is the kind of thing that we need to be able to make precise. We saw earlier this notion of ordered sets as well. I want to point out that this is the case if you say, I've got a collection of objects. These are the points of my set. And now for each pair of objects, I have a truth value. And it says if they are kind of related or if one is below the other. And so these kind of ordered sets we could think of as enriched in this weird category where there's just like two objects and an arrow between them. And then the composition rule says if A is below B and B is below C, then A is below C. It witnesses transitivity we saw. So that's another example. It's a kind of sort of zero-dimensional example of a category. And then, of course, if we go from one dimension of category up to two dimension of category, how does this work? Well, we had before a set of go over here. Before we had a set of objects and arrows between them, and then we had arrows between those arrows. And this sounds a bit familiar because really it's like saying we've got a category of morphism. And in fact, yes, every two category, or sometimes we might say bi-category, is a category enriched in cat. So it says we've got objects, this K0, I'm writing K for this cat category. And for each pair of objects A and B, we now have a category of morphisms. And we call that, again, KAB. And this just means that KAB itself has a collection of objects, which we could write KAB0 following the earlier notation. And these are the one cells or arrows of K, considered as a two category. And now for each pair of arrows, we have a set because it's a category. It has a HOM set. It has a set of arrows from F to G. And now, of course, these are the two cells, which are like, in the case of cat, they're the natural transformations. Is there a question? I sort of feel like I heard some.
Yeah, I think somebody was just crackling a cup. Actually, I don't think there was a question in the room.
Oh, okay. Okay. So this is nice. This is a kind of another perspective of taking this kind of basic notion of category, which is this really simple thing, and making it a bit more structured. Because we might have like extra data. This is data about how the arrows are related. And in general, we can use ideas like enrichment to add this kind of stuff, this extra data to morphisms. Now,
we do have a,
Sorry, I have a
so Toby, we do have a question here.
basic question. If you go back to the previous slide. So if you could go back one, there we go. You said you have a category of morphisms, but a category is objects and morphisms. So what does this language mean in this case?
Here, the morphisms, like they're the higher dimensional morphisms. So those are the two cells. So we had originally we had objects and morphisms, and I drew, this is just like a category. And now we have another morphism, and we could consider the collection of morphisms from this object A to this object B as a set. But now we think, okay, well, now we consider these elements of this set to be the objects of another category, and we fill it in. And as I drew earlier, we also have this rule that we need to be able to compose in this vertical way. And this is really the same as just the composition rule in this hom category. Does that make sense?
Yeah, I guess if I could just repeat back then. So the category of morphisms, the morphisms are the objects. The morphisms of the category of morphisms are the natural transformations.
Yes, in the case that K is cat. But in general, it might be another two category. Whenever you've got this kind of higher dimensional structure of sort of morphisms between morphisms, you can sort of write it in this way.
Thanks.
Okay. Right, so we can use this idea to sort of attach, data, sort of relational data to the morphisms of a category. So earlier, I drew this commuting diagram to say that this thing is a natural transformation. And this, like, the idea that this commutes is like some extra data. Like, it's something I've said about this morphism along the top and then the right, and this and the relationship with the morphism that's the left and then the bottom. And so it feels like this thing, the data that says this commutes, should be like the data of some enriched category. And indeed it is. You could say here, again, we have this kind of the hom object being a point of this weird category of truth values. And now it just says, okay, well, I can, if it commutes, I fill it in with like a tick or a truth value. And it says, okay, now this commutes. Now we've got like this high dimensional structure, the way that we fill this in. Or we might have like different ways of proving that this morphism is equal to this morphism. And so we might have a collection of different ways of filling this in. And so we might say that this extra data is a set of proofs. And indeed, proofs are kind of like morphisms themselves in a way that I might be able to have time to say later. Because, of course, you can sort of compose proofs by sort of cutting them together. And it might also be the case that actually this thing doesn't commute, but it sort of almost commutes. Maybe we could sort of measure the distance between these two morphisms. And then we could sort of fill in this box. The two cell becomes like a number. And so if we had another arrow over here and another two cell, we could say, oh, we add the distances to say how far this thing is from this further thing. And that says that the two cells commute. This makes it a two category, or like an enriched category in this sense. And if you keep going, like saying, okay, well, I've got morphisms between these morphisms. These things are proofs of the equivalence of the two cells or the three cells or whatever. This leads, you can sort of iterate that to it forever, and it leads to these things you may have heard of called infinity categories, and this other thing you may have heard of called homotopy type theory. And as I mentioned before, there's this kind of, if something doesn't quite commute, it's kind of like this high dimensional thing It's like a emergent property. So that's the kind of nice way that we can use this notion of enrichment to attach relational data to the morphisms of our category. So I mentioned this notion of distance, and in fact, metric spaces, so those are kind of like, those are spaces where you can sort of measure the distances between points. Every metric space is itself a kind of enriched category. So first of all, we need to say, what are we enriching in? Well, we're going to be saying we're enriching in this category, which is made up by the positive reals. We saw earlier that you can think of these kind of number categories as ordered categories, where the sort of objects are the points of here, the interval, and now there's a morphism from like a number A to a number B whenever A is greater than or equal to B. I also mentioned before that, there's this kind of way of sometimes putting things in parallel, kind of sort of dual composition, which is sometimes called a monoidal product. And in this case, so in the case of sets, I wrote down CAB times CBC, and this product forms such a kind of monoidal structure. And we need to be able to enrich in this category, we need to be able to do a similar thing here. And of course, these extended positive reals have such a monoidal product, which is given by addition, and it kind of preserves its order relation, which means that we can enrich in this structure. So, okay, what is a category enriched in the positive reals? Well, it has a set of objects. Okay, that's normal. But now for each pair of points, for each pair of objects, we just have a number, which is the object of this enriching category. And that number is just the distance between those points. And it has to satisfy the category rules. It has to have an identity arrow in which says, that 0 is greater than or equal to the distance. I mean, if we insist on our distances being, positive, then this just means that the distance from a pointer itself has to be, 0. And then we have this kind of triangular inequality, which just comes from the composition rule. This is just like CAB times CBC into CAC. So this kind of notion of category, or particularly enriched category, kind of comes up with this kind of surprising structure. This is this kind of synthetic idea. So a lot of stuff just kind of pops out of this kind of structure. And of course, we could kind of enrich again in the category of these metric spaces. We could say then, we have, this is this kind of notion of having distances between the arrows. Okay, how am I doing for time? Okay, but I think at this point, I want to talk about something a little bit different. Having mentioned this monoidal structure and having been talking about higher dimensional categories, I want to think about how we could sort of put things in parallel. So here, we had a way of putting morphisms in sequence. This says, okay, I do F and then I do G. But what if I also want to do H at the same time? This is like composition in one dimension, and this is like composition in another. It makes the objects and morphisms into a sort of monoidal structure in the sense of the kind of concept of monoid we heard earlier. And so that's why these things are called monoidal categories. And this often comes up in the context of thinking of morphisms as like transformations or processes, and the objects of the categories representing boundaries or interfaces for those kind of processes. And there are loads of examples of this kind of structure. So we could think of just functions in the category set as computations. So they have like an input data and they produce some output data. Or we could think of wiring diagrams where you sort of just kind of, you want to sort of put sort of machines together and have them kind of work in parallel. These things have a kind of monoidal structure. Or like generative models in computational statistics, or utterances of natural language where we can put words side by side and use grammar to sort of wire them together to get the kind of composite meanings. And so often we sort of want to connect these open systems together, which means composing them sequentially or in parallel, like I drew up here. And we can use this kind of monoidal, this kind of higher dimensional structure to do this. And this is one of the sources of these kind of graphical calculi, these string diagrams. So I mentioned that natural language gives rise to kind of such a kind of open system. We could think of words as kind of well, first of all, we have objects, and we can think of these as like grammatical types, like noun and sentence or verb. We'll see what verb might mean in a minute. I'm taking this from the work of Bob Cooker and colleagues, who's got a kind of body of work called distributional, compositional, categorical models of language, or DiscoCat. And here we can say, okay, we've got these objects which are grammatical types, and then we've got these kind of funny like triangle boxes. These represent like words, and we can sort of put them in parallel. So I'm reading the diagram sort of from bottom to top. And these are each like elements of these types. So types is a word, it's a noun, and clarify is a verb. We can think of a verb like this as a process that takes in two nouns and gives us back a sentence. And here I've just sort of bent around the wire that means taking in. So it kind of takes in this verb, takes in this noun, and takes in this noun, and then gives them back a sentence. And then we could think, okay, well, we put these words in parallel. Obviously, you hear me speaking word by word. But then there's this other funny stuff, this wiring, which is like the grammar, which represents the information flow of the meanings. So that's a kind of cognitive example of a monoidal category. This is like the parallel composition. Oops, I accidentally, okay. Sorry about that. Now, these things have some rules. If the slide changes. Okay, so these string diagrams, how do they work? Well, okay, so we have this other kind of product. So, we saw this kind of circle which represents kind of sequential composition. Well, here we now have this kind of times or like tensor symbol, which represents kind of parallel composition. And we can apply it to objects as well as just the morphisms. And it's the kind of the operation of the tensor on objects, which has this kind of monoidal structure. So in particular, if we tensor two objects together, we can sort of draw them as strings side by side. It's a monoid, so it has a kind of unit, and that's this thing we write I. And if we have this object I on a string, we just depict it as an empty diagram because it means kind of nothing's going on. But we can also draw the kind of sequential composition in this language too by reading up the diagram. So this G after F is like going F and then G in boxes. And as I said, this tensor is like going in parallel. So if we have two processes H and K in parallel using this tensor, then we just draw them side by side like this. So these are some examples. This is F into Y tensor Z. Oh, we've got two Y's coming out. This is like a state, it's sometimes called. So it takes in nothing and gives us back an X. And this is a thing that's sometimes called an effect. It takes in an X and does nothing. It gives us, maybe it does some internal computation, but there's no sort of observable output. And we can also depict like closed systems in this language. These are things which take no inputs and give no outputs, but they have some internal structure. Of course, if we sort of compose a state and an effect, we get something like a closed system. Sometimes these categories have extra structure, like we can say braid two of these wires together and then unbraid them. That makes it kind of symmetric monoidal like this. And sometimes we can say copy the outputs of systems, which is this kind of fork-looking diagram like this. This says, okay, given an X, I now get two X's. And sometimes these things come along with a kind of compatible deleting operation. When this axiom says, if I copy something and then delete one of the copies, it's the same as not having copied anything. And this one says, if I copy something and then copy it again, it doesn't matter which of the copies I copy. And so, there are all these nice structures and we want them to behave nicely. And so we put these axioms on there too. And it's these axioms which kind of makes them behave kind of, or makes us obtain some kind of powerful graphical language, because we can sort of do obvious graphical manipulations and they're sort of obeyed by the rules of the category. Now, you might notice that this monoidal category thing is like a two-dimensional thing. And then there was a two-category thing earlier, or a thing that I sometimes call a bicategory. A bicategory is like a sort of, it's a weak two-category in a sense that I don't really have time to explain. But we can turn any monoidal category into, oh dear, I don't know what that means. We can turn any monoidal category into a bicategory by doing this thing called de-looping. Now, we saw earlier that a monoid is just like a one-object category. Well, a monoidal category is like a one-object two category or bicategory. It's a monoid in the sort of two category of bicategory. And so it has a single 0 cell. It has 1 cells. These are the objects of the monoidal category. And now these are 1 cells, so they have to compose because, 1 cells compose, but they compose by this tensor operation. As we saw, we can sort of put wires side by side. Now we've got 2 cells as well, because we've sort of upgraded the objects to 1 cells. And now we're upgrading the 1 cells to 2 cells. And of course, the 2 cells are the morphisms of the original monoidal category, composed by this kind of sequential composition operator. And so we kind of get this duality, this thing that's sometimes called Poincaré duality, between the kind of diagrams of the monoidal category, the string diagrams, and the diagrams that we drew for the sort of 2 category story, where we fill in these cells. And the way this works is we take a kind of a space here, which we filled in, and we turn it into a box. And the boundaries turn into wires. So we can think of this as being like, we've got this box around F, and it takes in these wires. Now this is a box around G, like that. And so we can sort of translate between these 2 pictures. And, the great thing about category theory is that we can use the representation which is best for us, for our particular application. Now, I think, let me check the time. I think I've got a few more minutes. So I want to say a little bit about this picture that I drew earlier, because it's something that that's kind of relevant to the kinds of things that I'll be talking about, and maybe Jeff will be talking about later. And this is the idea that, sometimes we want the choice of morphism. So here I drew a morphism. It goes from F, it goes from X to Y. But sometimes it might depend on some other process. It might be controlled by some other thing. So for instance, if you're interested in neural networks, you might have a kind of learning process which changes the particular morphism. Here, the morphism is the neural network, but it's parameterized by this learning process. So that means it takes in this extra data, its weights. Or if you're thinking sort of more biologically, you might think of neural circuits. And here the parameter object is the kind of synaptic weights. And then there's this control process, which is synaptic plasticity. And there's a nice thing we can do in any monoidal category, which is if we have like a morphism like this, which takes in two things and outputs one thing, we can sort of bend this wire upwards and sort of put it in a 3rd dimension. And that's all that's going on here. We're just sort of thinking of this thing as like being parameterized by this other input. And this is called the power construction. And it turns every monoidal category C into what's called a monoidal bicategory. So we've again got now some notion of 2 cells. And what are the 2 cells? Okay, so first of all, what are the 0 cells? Well, again, the objects. The 1 cells, or the morphisms, are just morphisms of this kind that have a choice of parameter space, and then they have a parameter input and an X input, and it goes back and Y. So this is like this 2-wire box picture I drew. And we can compose them sequentially by sort of taking the tensor of the parameters. And of course, we can sort of compose them, in parallel, like we might expect. E prime like this. That's nice. So it's kind of got this monoidal structure. And it also has this kind of higher dimensional structure now too, because we could put some other box up here, say. So we've got this kind of 3rd dimension, as I mentioned. This is the thing that comes into the diagram. And these things we could think of as like reparameterizations, because they might change the parameter into something else. And this kind of thing turns out to be really useful in talking about systems like cybernetic systems, which have this kind of environmental interaction or environmental control structure. Okay. So I'm getting to the end, I think, of my time. I just want to recap briefly and then mention this 3rd ingredient, which I may not have too much time to go into. That's kind of higher categorical structures let us express clearly and precisely the compositional structure of systems and concepts and processes. And that categorical tools enforce this kind of tight discipline because we can't compose things that sort of don't really make sense. If I've got a couple of minutes, which I think I do just about, I want to say a little bit more about this 3rd magic ingredient of categorical methods, this notion of perspective or context, because it's really at the heart of the kind of universal constructions that Steve was talking about, kind of maybe slightly paradoxically. How you see the world, of course, depends on where you view it from, and that's really at the heart of what makes a lot of category theory really powerful. You might know the kind of parable of the blind man and the elephant. You know, they all feel a different bit of the elephant and say, oh, it's something different from each other. And actually what we need to do is kind of integrate all of their perspectives to get a good sense of what the elephant's really like. And this is this thing called, by some people, the kind of Yoneda perspective. So the Yoneda lemma, a thing which I'll introduce momentarily, is the kind of fundamental theorem of category theory. It's the kind of this dual statement to this importance of perspective thing. It's a statement that to know a thing is to see it from all perspectives. And then the Yoneda lemma is kind of, as I say, this fundamental theorem, which is the formalization of this statement. There's not going to be time today to sort of explain this formal statement, but slightly more precisely, at least, it says that you can identify an object in a category with the collection of the ways of looking into or out of it. And as we mentioned earlier, it's kind of the morphisms of the category that are the important things. The objects are kind of just how the morphisms connect to each other, and we can sort of somehow forget about them if we have this morphism data. And so this Yoneda lemma, it's true for all categories, but it's also familiar to us intuitively in life and in science, right? We know a place by how to reach it. I mean, if you know how to get to somewhere, you know where that place is. This is common idea in linguistics that you can know a word by the company it keeps. And this has been really powerful in sort of computational linguistics and machine learning these days. And similarly, we can kind of know what a concept means by the way it's connected or connoted with other concepts. I mean, there's lots of great material on the Yoneda lemma. I'm sure we'll put some of it in the bibliography. I don't really have a lot of time to say much more about it just now. Except I want to say that it's at the heart of kind of universality. I want to kind of wrap up, and so I won't say an awful lot.
I think, Toby, I think you ought to think about wrapping up so we can give you and Jeff both some more time for your second portions.
Yeah. Okay, well, let's see. This is probably my last slide. But yeah, I mean, I think I've said everything I need to say. Yeah, so let's leave it there.
Okay, thank you very much, Toby. That was really a nice overview. I really appreciate that. So while Jeff is coming to the podium, is there anyone, I guess you'll have to release control of the screen there for a sec. Anyone in the room want to ask a question, or anybody online want to pipe up with something while we're transitioning between the two talks?
Next door.
I thought we had a question here, but it was actually just filtering in from next door. I was confused. Okay. Alrighty. Are you? So I guess we'll switch to Jeff's topic. So hopefully you'll see it all on the screen. Jeff's going to talk for about the next 45 minutes or so here, and then we'll come back with Toby for the closing talk, and then for those of you, it looks like we're going to run pretty close to the end of our, actually, maybe I'm doing better on time than I feared, but okay, we'll let Jeff go now, and he's got about 45 minutes or 50 minutes or so, and then we'll come back with Toby, and then we'll have a few minutes at the end for our concluding remarks.
Thanks, yeah. So as I was mentioning before at the beginning, I sort of often worked in pure mathematics. It's only recently that when I was doing some stuff thinking about derivatives and what they kind of mean categorically, that I found some people in the applied category theory community were using some stuff I did about derivatives to try and understand what's going on a little bit more with machine learning and deep learning and things like that. And so we're really just starting this. This is just to give you an idea of sort of where we're going with this stuff, but you already start to see some, I think, interesting categories, and you'll see a functor that appears as well in the story. Just give you perspective about how you can use some ideas in category theory to start talking about some things that are happening in machine learning on things. And one of the sort of perspective I'm going to take is sort of in a very general sense, how can we represent learning categorically? I'll give you one answer to this one interesting category you can build, which kind of where the morphism represents some kind of thing which learns, some kind of thing which does an action and then can learn from that. And it's a very general sense of this, but I think it illustrates an interesting perspective of learning, this kind of bidirectionality of learning, where you do some action, get some feedback on it, and then change your internal state based on that. So I'll talk about sort of action takers versus learners, talk about a category of learners. And then what I'm going to transition to talking about is the derivative as a means to construct a learner. And this is sort of at the core of some of the things we were doing, that when you take, one way you can think about taking the reverse derivative, and I'll talk what I mean by that, is it's a way of constructing something that can learn, something that can get some feedback on its action and update its internal state. Sorry, I didn't mean to keep on hitting this thing. And then I'll talk about sort of conclusion and some pointers to research. And one of the claims I want to sort of take away from this is that at the core of many machine learning or deep learning algorithms is actually a functor. There's it's a passage from one category to another, which is used in a very important way. And this observation isn't new. It was, there's a paper by David Spivak, Brendan Fong, and Remy Tereus talking about the title is backprop as functor, so backpropagation as a functor. So taking that idea and change it just a little bit, but it's sort of a very interesting idea relating these two sort of concepts. Okay, so just very generally, you can think about some entity that takes some action as a function. It has some kind of inputs to it. Maybe it's a set of pictures it's looking at, and then maybe it looks at those pictures and it says what probability it thinks that picture contains a cat, or maybe it's, inputs are, some kind of thing that it does a process with and outputs something. So just very generally, we're thinking of some kind of entity that takes an action as just a straightforward function from A to B. So, or maybe more generally, we could think about it as a morphism in some category. But for now, just think about, like, say, as a function, some inputs and outputs. But let's think about what would it mean for such a thing which can take some action to actually learn from or to learn what happens. So imagine that in addition to our sets of inputs and outputs, we have these set of things and the set of functions between them, which representing the actions we could take. For every set, we also have some associated set of actions, sort of ways to update our inputs or our outputs. So we'll have some kind of way of, when I take an action, I can be told, oh, you were wrong about this. I take an action, I say, I think this picture contains a cat with probability 0.25, and actually really, it did contain a cat, so that probability was 1. Now we can think about that as an update on the output of our function. Right? We've taken some function, we took some input to it, we gave to somebody an output, they told us how wrong we were, we then take that output and do something to change our input, change sort of our mental state, change the setup of our, the weights on our neural network, whatever. There's this kind of, again, this bidirectionality process. I take an action, I'm told how wrong I am, and a learner can take that feedback and do something with it to change their internal state. So again, when I think about when I perform an action at some point A, we get so it should be an output, f of A and B. We're then told that we need to update this to get the actual value. And a learner, what they can do is take that update on the output and use it to make it an update on their input. So learners should be able to take this update action from the output and know how to use it to update their own state, represented by giving a point of the updates for the input set. So just summing that up, a learner would have not only a way to take actions, an ideal sort of learner, idealized learner, but have a way to take actions, but also when they take an action and they get some feedback, they have some way of updating their internal state. And so we can represent that, the action itself as a function from A to B, and the update they could make to their internal state as a function from this pair of things. So we would take an input of A, does an action, receives a update to the output state, that's an element of U of B, and gets back an element of U of A. So it's kind of going backwards, right? It's sort of a mixture of forwards and backwards, because it takes an input and an update to the output set and gets an update to the input set. Again, sort of representing the bidirectional nature of learning. Now, what's really cool is we can make a category of these things. So we've been talking about categories, so we have to have objects, arrows, composite maps, identities, things like that. So an object in this category is going to be a pair of sets. Every object is not just a single set, but a pair of sets. The first part of the pair representing the sort of points of that set, and the second element of the pair representing the possible ways we can update those things. we're keeping it very general. So these are both just two sets really, but we're thinking of the first thing as the inputs, and the second thing is the way we could update. And then an arrow consists of two parts to it, not just a function from A to B, that's part of it, but also this update thing, which goes from A cross UB to UA. So an object consists of two things, two sets, and arrows also consist of two things as well. And again, categories are very general. The objects and the arrows can be anything we want, as long as we can compose things and they satisfy the rules, as Britt was mentioning before. So in this case, our objects are pairs of things, our arrows are pairs of things. And the second part of the arrow is what's interesting, again, because it has this kind of mixed nature. It takes in something in the input and an update action in the output, and gives us an update action for the input. So that's the objects of the arrows. I got to tell you what the identities and composites are. So the identity is straightforward. The identity on A, comma UA, that's an object in our category. It has to be two things. It has to be an arrow in our category, so it has to have two parts. The first part has to be a function from A to A. We'll just take the identity function, which does nothing. And then the update action would just take a point and an update action and just give you back that update action, so it wouldn't do anything. More interesting is the composite of two maps. So now, if I'm given kind of a map from AUA to BUB and a map from BUB to CUC, so an FUF and a GUG, I have to give some composite, a pair of things. So I have to give a composite sort of action and a composite update thing. And the composite function is just compose the functions and nothing special there. The composite update is slightly more interesting. So I've just written it out sort of in set notation, but I just want to think about it for a minute. What I have to give you something which takes a point of A and a update action on C. So I can use the pointer here, at least for people in the room. I have to give a point of A and an update action of C and give you back an update action of A. That's what I have to do to give an arrow in this category to give you the update thing for this. Well, I can't just directly use the update for G and the update for F because they don't sort of match up quite right. But what I can do is take the update for G. So I apply F to my point A, that gives me a point of B. Then I can use the update action for G, which needs a point of B and an update action for C. That entire thing is an update action for B. Now I apply A at the point and the update action that I got from this kind of composite thing. So the composite is sort of interesting. It's not completely straightforward. But really, if you sort of mess around with it, it's the only thing that could possibly work. And again, it has this kind of bidirectional nature. To compose the update actions, I need to use one of the actual actions and then use the update for G and then go backwards and use the update for F. So here I noted that the composite update kind of goes backwards. First it uses the update for G, then the update for F. But I also wanted to note that it's also using the function part of F. So it has this kind of mixed nature again. And sort of hinting what I'm going to talk about later, this is really what's happening with backpropagation, where you sort of do a process forward and then you update all your things in a backwards kind of way. And it's also, as we'll see, related to the chain rule. This kind of thing with a UG with an F and then a UF. Remember the chain rule, the derivative of F composed with G, F prime of G of A times F prime of A, or depending how you set up the order. That's actually really one way it's going on here. So this, going back for a sec. So this gives a category. Now I have to check the rules as well, as Britt mentioned. I have to give identity composition, but I have to check associativity and I have to check the identity rules. But those all work as well. It takes a little bit of work to check them, but it does work. So you do have a category here. And what's interesting already about this category, first of all, it's an interesting category because it has sort of mixed nature of, it has both forwards and backwards kind of movement to it. But it's also been discovered and rediscovered many different times. And there's a really nice blog post by Jules Hedges, with the reference down here, called Lenses for Philosophers. And here he gives about 13 or 14 different times this category has been discovered and rediscovered. And it appears to be useful in lots of different places. So there's one of the big places it's been used a lot in database theory. These things I'm calling learners are all called lenses. And actually, that's a more common name. So if you're looking at literature about these things, most people call them lenses because that's where they originally come from in database theory, where you have some kind of database and you view the database and maybe you make a change about how you view the database and that changes some stuff back here. It has this kind of bidirectional nature to it too. So called lenses or bidirectional transformations. The standard name nowadays is called lenses, but I think if we were, going back, learner might be a better name. There's various variants. Yep.
Sorry, we have a question here
Yep.
in the chat. Mattes Pink is asking, why will A be updated? is it related to the idea of active inference?
Why A updated?
Yes. Why will A be updated?
So yeah, it's like we want to think of changing somehow our internal state, how we want to do our actions, right? Once I've received feedback on an action and told I was wrong, I want to sort of change my internal state. Okay, maybe I have to readjust how I'm thinking about the world, and I change a little bit about how I'm going to take my next action, basically.
And oh yeah, no, it was a commentary by Toby, complementing your answer. So if you think about backprop, the idea is that the backward pass sends back feedback about how the inputs could have been better. It is like an error or difference.
Yeah, I mean, there's also a little subtlety that I'm kind of overriding here. I'm kind of conflating both the internal state of the person that's taking action as well as the input that they're receiving to the action. So the full story is a little bit more subtle. You have to use the kind of category of parameterized things as Toby was talking about. But for now, I'm just keeping it sort of very basic, where I've got both a set and a set of update things. And I'm not even sort of applying those updates, just thinking about generally, I get some feedback on my output. I'm going to make some kind of change. I'm going to do something different on my input. Are there any questions there?
No, thanks.
Okay. Yep. So there's lots of variants of this category of lenses, things called optics, and they're used a lot in functional programming as well. Jules Hedges, who's writing this blog post, is used to study open games. And you can sort of imagine where games might be used, right? You take some movement in a game, your opponent does something, and then you make a response, right? That's kind of that bidirectional nature. I do something, my opponent does something, and then I make a response to it. One of the original sort of categorical things, though not, again, sort of in isolation from all the other things, Valeria de Paiva used them to study Gödel's dialectical interpretation of logic from a categorical viewpoint. So she made a category which sort of encompassed some of the things that were going on in Gödel's dialectical paper. And in essence, one of the things she was building was this category of learners, as I'm calling it here, has sort of a bidirectional nature to it. And what I think is interesting, one of the things, as I was mentioning at the beginning, I always think about interesting is category theory. It allows you to make these kind of connections. These things which would seem to be in isolation, game theory, database theory, functional programming, logic, at their core, there's some similarity here. There's some categories that are appearing that are the same in all these places. And I don't sort of know yet what to do with that, but it's interesting that these connections one can make these connections because category theory is so general. Okay, so I was talking about having a learner. It'd be nice to have a learner to learn something. So a learner can receive some feedback about what it's done and make some updates to what it should do in the future. So it'd be really nice if we're given some kind of just way of doing actions, can we canonically turn it into some kind of thing which can learn? And we could maybe phrase this categorically. Is there a functor from the category of action takers to the category of learners? Maybe a non-trivial functor, as mentioned before. There's generally lots of functors between two categories, but say, is there a faithful functor from the category of action takers to the category of learners that might have other nice properties as well? And it turns out that using the derivative will give us a way to go from the category of action takers to category of learners if we sort of make these things, add some conditions to what we're doing here. So suppose we can represent our inputs and outputs as subsets of Cartesian spaces Rn's. So maybe our functions are now defined on some subset of Rn and give us some subset of Rm for varying n and m. And what are we going to let to be our possible update actions? We'll use vectors to be our possible update actions. So if imagine if I'm given I make some claim that something is the following value, but actually we're told it was this value instead. Well, that vector can kind of represent how far off we were. So we can represent our update actions as the points of Rn, our functions as things from subsets of Rn to subsets of Rm. And suppose the action takers we have are all differentiable functions. What we can do is make the matrix of all partial derivatives, but sort of the transpose of it. So that'll make it nice to go backwards. So just a simple example, if we have this function from R3 to R2, taking x, y, z, and giving x squared plus y squared and 3x sine z. What we're going to do is build the transpose of the Jacobian of f. So take all the partial derivatives of the first function and put them down in this column like this. So derivative of this with respect to x, 2x, this with respect to y, 2y, do this with respect to x, y, and z. So 3 sine z, 0, 3x cos z. So this is the transpose of the ordinary Jacobian. And so we've taken our function, made this transpose of the Jacobian. And if we evaluate that matrix at a particular point, we get an actual matrix of numbers. We can then apply that to a vector in our codomain space. So if we apply this vector, so this matrix to the point -1, 2, we get a vector in R3. So we started with a function from R3 to R2, and then by using this kind of transpose of Jacobian, the reverse derivative, we get a way to get transport a vector in R2 back into a vector in R3. So getting some kind of update, some kind of error on our codomain, we can transform it back into an error in our domain. And this is exactly what we need for a learner, right? Given a point of the domain, that was our point here, and an update in the codomain, this vector here, we can get an update in the domain. Now you could also choose the ordinary Jacobian to go forward, right? To go from a change in the input to a change in the output, but we want a learner, and we can do that by taking the transpose of the Jacobian. So just to sum up what we have there, we started with a function like this, and we took the transpose of the Jacobian, evaluated a point, and taken a vector, gives us a vector in R3. So we take some point of our input space, take a change, some kind of update to our output space, and we get a change to our input space. So altogether, we've got this map going exactly the type we wanted, from points of the input space, changes in the output space, to points in the input space. And so that would be a way we could get this kind of backwards process that takes exactly the kind of type of maps we want. So now we're claiming we actually have a functor from this category of differentiable functions. So our objects are these subsets of Rn's, our functions are differentiable functions between them. Our learners are a slightly more complicated category which has both an action and an update part to it. And what would we send an object to? Some of our functor has to send objects to objects and arrows to arrows in a way that preserves all the data. So, whoops, given a object here, we'll send it to the pair, just like we kind of indicated before, keep the same thing, but our updates are the possible vectors in Rn. And given a function, we send it to the pair, we keep that f around, that's our action, and the rf is going to represent our update thing. Now, to be a functor, it has to preserve identities and composition. It has everything, as Toby is sort of mentioning, things are, things have to be well typed. We have to preserve the basic operations that are around. So does this preserve composition? And let's take a really simple example, right? We start with just functions from R to R, f from R to R and a g of R to R, just so we don't have sort of multiple variables. And what it would mean to preserve composition is if we first, if we apply this process to both f and g individually, so we do kind of the reverse derivative thing with the derivative there and then g, and then compose them in the category of learners, which has that kind of weird composite rule which uses both a forward and a backward pass. What would we get? We get something which takes a point like this and applies this rule that I mentioned before. And this is really the only rule we could do, sort of make a reasonable category out of it. And so that would be, we have to do the reverse derivative at g of g at f of a with w as our input. And so that would be g prime of f of a dot w. Now we apply the rf as our update function. And so we get f prime of a times g prime of f of a times w. That's one way of doing things. We could do the functor first, then compose them in the category. Or we could first compose the two as functions, composing them in the first category we started with just the differential functions, then apply the process. We would take a point like this, and this rule would say, do g compose with f prime at a dot w. And this is right here is where we're using the chain rule, right? G composed f prime of a is g prime of f of a times f prime of a times w. So that passage to that passage is the chain rule. But these are exactly the same here. So the fact that this is actually a functor from this category of things which can take actions to things which can do some updates, the fact that it preserves composition is exactly the chain rule. It's sort of nothing more or less than the chain rule. And this here, I've given this for functions from R to R, but it works more generally for functions from Rn to Rm and composing a couple of those. So functoriality is precisely the chain rule. And so it's a different way to think about the chain rule. But I mentioned this before, I sort of jokingly say when I teach calculus classes, I should just, teach them all category theory first and then say, oh, the chain rule is obvious. It's just, a functor. This is functoriality. But I don't think that would make life any easier for poor first-year calculus students. But I think there is something nice, really nice about it. Again, we're kind of, I was talking at the beginning about a lingua franca, right? A sort of universal language. And if every part of mathematics and every part of science has its own little sort of things, it's really hard to make these kind of connections. But realizing something as fundamental as the chain rule is actually a functor between two different categories can help you kind of compare these different approaches and kind of make common comparisons between what's going on in different areas. So the chain rule isn't sort of just something off to the side, it can be seen as a functor. Why? So why one thing about why is it knowing it's a functor useful at all? Well, it's really just what's going on with backpropagation. Oh, yeah. Yeah. Mm-hmm. Yeah, it still works. I mean, it kind of, yeah, it's a good point. Like, because maybe we're worrying about sort of composition of matrices not being, yeah, kind of symmetric. Yeah, I think the kind of way I wrote it here made it look like it's sort of dependent on the fact that this multiplication is commutative, but no, it works absolutely generally, yeah. I mean, if you look at multivariable calculus textbooks, they'll talk about the chain rule for multivariable functions. That's essentially what this is right here. Yeah, that's a question though. Yeah. Yeah, that's a really good question. I was going to talk about that at the end. Here, I'm just sort of talking about one update thing at a time, just using the reverse derivative. But typically in kind of machine learning things, maybe do multiple update steps at once, then batch them all together and things like that. Certain things that end up being functorial and certain things not being functorial. But if you sort of set things up right, you can make lots of functors which do work. So yeah, it's a good question. If there are questions. Yeah, so really, I mean, often when people talk about backpropagation, they always say, okay, at the core of what's going on with backpropagation, when I have, a neural network which is composed of a bunch of little, whole bunch of little bits, and this kind of computation feeds into this bit, and then this bit feeds into this bit, and this bit feeds into this bit, and eventually you get your answer, and it tells you, oh, this is a cat. The fact that it's composed by all those little bits, if I want to update the whole network, what I can do is sort of update each little bit backwards. That's going on with backpropagation. That's exactly what we're sort of expressing here categorically. The fact that this kind of update process can be done by all those little updates is functoriality, that to get a big update, I compose a bunch of small updates. That's what's going on. So, people will write backpropagation is really just about the chain rule, and we're sort of rephrasing it here. It's really about functoriality. It's really, it can be thought of as a functor between two categories. Now, of course, as I was mentioning before, there are lots of functors out there. So maybe there's some additional properties which make this nice. Just a couple points of why this is nice. If the input update is 0, then the output update will also be 0, because if I input sort of a 0 into that, multiply it by that matrix, I get 0. So if I got the right answer, I don't need to make any changes, and it's linear. So if my update was a sum of two things, then I can make that update by summing the result of updating for U1 and for U2. So in addition to be a functor, you can also phrase it that it's sort of an additive functor as well. You can talk about Toby is talking about enriching the categories. So in this category, you can add maps. I can add two differentiable functions, still get a differentiable function. And this functor is actually preserving some of that additive structure as well. So, mentioning earlier about functors don't have, they're preserving some things, maybe not preserving all the things. There are other things this is preserving as well, which one could express sort of categorically as well. But I think one of the core things really is just being a functor is sort of really just what's going on with backpropagation. Yeah, so this is just sort of this is a core of the gradient-based learning process, but there's also additional components to it. You might vary how you measure the degree of wrongness of an answer. People use different loss functions. You may vary how large of an update you make at each step. Sometimes initially you want to make larger updates, then as you get closer, maybe you make smaller updates, you change the learning rate. You might want to make changes after seeing results of a number of different feedbacks, and or sort of keep track of how much was updated previously and use that. There's kind of these momentum methods. So in this talk here, I'm just giving you sort of some core points. In this paper, Categorical Foundations of Gradient-Based Learning by myself and some others, we talk more about how to fit these other parts into a categorical setup as well, and sort of at which point you're having a functor, at which point, which things you can sort of vary. And part of our goal was to try and show you can vary these different components and still get some nice sort of categorical setup for what's going on. But I think at the core of it, that there's this kind of category of lenses or learners, which has this kind of backward forward process. And at the core of it is this functor. Yeah, so just wrapping up. One way to generally represent some kind of thing which learns is an arrow in this kind of category with a bidirectional nature. And I think it's a really interesting category. I was sort of surprised how interesting and useful it is. And I think there's a lot more that can maybe be done with it. And it's interesting that it shows up in lots of different places as well. Maybe it's not so too surprising because, having a kind of backwards and forwards process is really key in lots of places. One way to go from just sort of a straightforward something which takes actions to something which can learn, something an arrow in this category is provided by this reverse derivative operation. So this kind of then needs to ask you other questions. Can there be other ways we can build learners? Sort of, there's a question about that as well earlier. This is at the core, maybe of many processes, is using the reverse derivative. One reason that it works so well is because it's a functor, but could there be other ways? Is the reverse derivative, I haven't thought too much about this, but interesting to explore, is the reverse derivative kind of the nicest in some sense? Is it kind of, Steve was talking about universal things, which are sort of the best thing, the best possible solution to things. Can we set something up to show that this kind of reverse derivative is the best possible version? It's sort of getting you closest, fastest to the possible answer. I don't know, but now we can sort of ask these kind of questions now that we've made this kind of setup and put it in a categorical framework. So as Britt was mentioning, we're going to give a whole bunch of links to categorical resources and papers, but here's just a few specific to this talk. This paper by Brendan Fong, David Sivak, and Remy Tereus, Backprop as Functor, was really an interesting sort of first step into this. We took some of those ideas and kind of split off different parts and made it slightly more general as well. But really the start of this idea of even being able to talk about any kind of categorical things with supervised deep learning, machine learning was first here. And there's a really nice survey paper, actually, a bunch of other survey paper bringing together, sort of discussing papers that people have written about category theory and machine learning. So this is a paper which is quite long, but shows all different perspectives. I think Toby's going to talk a little bit about some other perspectives as well about sort of relating category theory and machine learning. And as I mentioned in the beginning, we're really just at the start of this process. We're starting to see what are the categories, what are the functors that lie around. And Britt was talking about that. In some sense, that can sometimes be the hardest step. Somebody's mentioning that earlier, like, I have many different complicated models of the mind. Even just understanding what the right categories are can be difficult. We're starting to make those first steps, but there's lots more potentially to do. I think that was all I had. Thanks.
Now I feel bad about cutting Toby off slightly, since you were so efficient with your time. So let me ask one question I had, which I hope makes a point. Can you go back to where you established first the composition rule?
Yep. For the updates?
Yeah. So yeah, and you said it's kind of a complicated composition rule, but it's sort of the only way it can be.
Mm-hmm.
And I want to know if you agree that this is an example of the statement I made before, like that sort of sometimes there's only one way to do things. And so the harder part may be sort of in the setup, but it seems like this rule was discovered not because you had this brainstorm that like, this is how reverse differentiation should take place, but once we have this set up, let's just apply the steps we have to apply and find the way that we can make a sensible composition. And then that will now show us the way forward.
That's a good question. I don't remember sort of the origin of which came first. It's probably, though, the second one. Yeah, it's just like, let's set up things to talk about things very generally, and then let's see what we have to do mathematically. And then often we'll go back and say, oh, this is actually what's going on in some sense. That's often what happens. I think that's what happened in this case too, yeah.
Do we have some more questions from the room here? Yes, please. Can you, just yell at the mic at least.
I have a comment. I'm not sure I can turn it into a question, but it's really a comment. With backprop and all of that, there is this important element that the there's this negative sign, you change the weights as to make the error on the next time less than it was before. And it seems to be only implicit in all of this that you're showing. So you have all the derivatives, but in principle, nothing that is on the board says you have to take care that if you do this exact same input again, the error on the second run will be less than that on the first.
Yeah.
And you need this to get convergence
Yeah.
and all that. Otherwise, you're magnifying the error.
Yeah.
And I think a learner that magnifies errors still is a category, but it won't converge in practice. And
Yes.
so that seems like an important.
Yeah, so that's one thing I was mentioning about, it would be nice to have, well, I don't have a slide about it, but it'd be nice to have some kind of theorem or result that says that this is a universal learner in some sense, that it is getting closer and closer to the correct answer. And we don't have a precise statement about that, but doing this kind of setup, maybe we can make that, even that idea precise, that this process is the best possible or is getting better and better at each point. It isn't, so my point is, it's not in this setup right now, but there's the potential to be able to talk about it because we can talk about universal things in a category, and those are kind of the best solutions to problems. So we can try to prove that kind of statement, that it's a best solution to some kind of problem like that. That question? Oh, you might want to just, yeah. Or go to the mic. Just they can hear.
Yeah, the idea is for the online people, they
Yeah.
can't hear the questions if we don't use the mics.
Yeah, no, I'm just sort of continuing that conversation. Isn't the question of whether the learner is going to get to the right answer, doesn't that just depend on what the updates on B look like? And those are sort of given from somewhere else, not from these learners in this place of.
So
where
yeah, I
learners
mean, you have to be
right?
careful because yeah, it also the overall process depends on, which, if somebody's telling you you have the wrong answer when you have the right answer, that would be a problem too, right? So you'd have to set it up so that, supposing you're getting sort of the right updates on the output, that you will converge to those right outputs there. So you can kind of, I think, kind of push that problem away by assuming that somebody's giving you the right outputs and prove that this thing converges to the right output in that
The
case.
stuff like the direction, that the vector goes would be sort of a property of the update on B. wouldn't it?
Please go. I'll ask while you're getting up there to make sure somebody online has a question. It's hard for us to see you. So if you don't just sort of insert yourself, we'll just keep taking people in the room. So please do speak up if you're online, you want to ask a question. We've got one coming from the room now, and then when it's done, please ask.
Great. So it seems like a lot of the work that you're describing here and that you kind of referenced, excuse me, at the end, is focused on cases where we can compute a gradient in some kind of real value space. Do you have any idea how you might take this approach and apply it in a case where we're doing something like symbolic search or rule learning or something like that?
Yeah, I mean, that's short answer is no, not myself. I think other people have been looking at that. I think in that reference I put at the end, people are looking at it sort of more generally as well. But I think in all those cases, this kind of core idea of the learners and having this kind of learners or lenses, these things which have a forward thing and the backward thing is sort of a constant between all those. So I haven't done it myself, but I think there are people that are still using that lens idea and trying to construct functors to the category of lenses, for example, in other settings as well. That wouldn't use the gradient. Yeah, Toby probably say more.
In the context of reverse derivative categories, aren't there lots of examples of differential structures? Well, at least I'm aware there are some examples of differential structures which behave like derivation, where they're not kind of classical calculus kind of things. I think I came across something to do with Boolean circuits, which had some kind of differential.
Yeah, so
and then you could do all of this, but you're just kind of.
Yeah, so that's a good point. So in the paper, we were actually doing it more generally than I'm talking about here, not just about differential functions between Rn, but in a general context of a reverse derivative category, which is a category equipped with some kind of operation which behaves like the derivative, or has axioms to make it behave like the derivative. And yeah, we have some examples there, like Boolean circuits, such as 0-1 things, and they're sort of they have a reverse derivative structure, and so they have all this kind of all the structure I'm talking about here also works in those examples as well. To my mind, that's still kind of like the ordinary derivative, just applied in kind of a Boolean setting as opposed to a smooth setting, but it is different. So that's, yeah. Thanks, Toby.
Do we have some online questions that people would like to ask or comments to make?
None for now.
Okay, so hey, Toby, remind me, so what time do you think you need for your next presentation?
I can take arbitrarily long.
Okay, could you put any, okay, so could you put a little distribute? So
I
I
mean,
guess
I
what
could
I think I
take-
did a little, I think I'm a little off on my timing. I think the coffee break was supposed to be available starting at 3. Is that what people remember from out there? I was just thinking I might be able to give people a break until like 10 after 3 if they wanted to try to find a cup of coffee, and then you would pick up, and that would still give you plenty of time to sort of lead till 4, a little after 4, something like that. Is that possible or not? What do you think?
That'd
on
be
your
fine. The more
arbitrarily
time,
long-
the better. But I mean, I'm happy for people to get coffee.
Well, if I let you start at 10 after 3, you have potentially up to an hour and 20 minutes to do. Is that?
Oh my God. Okay, that's lots. I won't. I will
Okay.
try not
Okay.
to take
So
this long
all right.
time.
So we are going to. So right now, my watch says that it's almost 10 to 3, and we'll come back at 10 after 3 to pick up Toby's last talk, and then whatever time he doesn't use, we'll try to encourage you to help us build a little bit of a annotated bibliography online and a place to share some resources for us as a community, and then we'll close up. Okay, so we're taking a little break.
Cool. I will say I'm going to be talking about lenses.
He is going to talk about lenses, and in some ways it's related to a lot of the concepts we've heard, and I think it's, yeah.